Hello. Hello. Sir, can you hear me, my voice?
Hello, hello. Sir, good morning, sir. Prashant, sir.
Ha, good morning. Very good morning, sir.
Sir, shall we start?
Yeah, with your kind permission, you can start. Sir, my camera is not working. Is it okay?
Yes, sir, no problem.
Yeah, thank you.
The capacity to learn is a gift. The ability to learn is a skill. The willingness to learn is a choice. A very good morning to all of you. With the motivational support of the Chief Patrons of the FTP, Dr. A.J. Shetty, President of Lakshmi Memorial Education Trust, Mr. Prashant Shetty, Vice President of Lakshmi Memorial Education Trust, let us begin today's session of FTP. We have with us today the resource person, Dr. Prashant Kumar H., Assistant Professor, National Institute of Technology, Karnataka, Principal of AG Institute of Engineering and Technology, Dr. Shantaram Rai C., Vice Principal, Dr. Nagesh H.R., revered HODs of various departments, Dr. Gnani Swarnath Satapathy, HOD of ECE, Dr. Anthony P.J., HOD of Computer Science and Engineering, faculty members of various departments, all the participants from various institutions, and dear students. I, Sahana K. Adentaya, Assistant Professor, Department of Electronics and Communication Engineering, take the privilege to welcome each one of you for the 4th day of 5 days faculty development program on recent trends in medical imaging and communications, organized by the Department of Electronics and Communication Engineering in association with the departments of Computer Science and Engineering and Information Science and Engineering. May I now request Professor Prakash K. Shetty, Associate Professor, Department of Electronics and Communication Engineering, to welcome the gathering and introduce today's resource person.
Hello everyone. I hope I'm audible.
Yes, sir. Yes, sir.
Yeah. Very good morning to one and all participating here. Our respected Dr. A.J. Shetty sir, President, Lakshmi Memorial Education Trust, Vice President of the Trust, respected Mr. Prashant Shetty sir, our beloved Principal, Dr. Shantaram Rai sir, Head of the Department, Dr. Gnani sir, respected HODs of all the departments, my dear colleagues, invitees, participants, and dear students. I deem it a great privilege and pleasure to welcome and introduce today's eminent speaker, Dr. Prashanta Kumar sir, who is currently working as Assistant Professor in ENC Department of NITK Surathkal. Prashanta sir obtained his bachelor degree in Electronics and Communication Engineering from Malnad Engineering College, Hassan, where he passed in the year 1998. After his engineering, he got enrolled into MTech in the ENC Department of MIT Manipal, which he completed with very high accolades in the year 2001. He then joined the same department at MIT Manipal as a lecturer in the same year, and he got successive promotions which landed him up into assistant professorship within a short span of his service. He joined PhD full-time at NITK Surathkal in the year 2007, which he completed in the year 2011. He then joined NITK Surathkal, and till date, he is serving there as assistant professor in the Department of ENC. Dr. Prashant sir is an eminent scholar and a very popular professor in his department who is liked by everyone, both his students as well as colleagues. He has keen interest and carries out research in many of the key areas of electronic communication, such as wireless communication, signal processing for communication, error control coding, and RF electronics. He has published several research papers and presented his research in numerous research conferences. His research contributions can be summarized as follows. He has published 13 journal papers, almost all in a very reputed international journals, research presentations in 10 international conferences, many of which have won him the Best Paper Awards. Sir has published 3 books along with internationally acclaimed authors. He has associated with the authors as reputed as Manolokis and Provakis and Thomas Floyd in the fields of digital signal processing and electronic devices respectively. With this brief introduction, I am welcoming and presenting before you today's key speaker, Dr. Prashanta Kumar sir. Welcome and take over the session, sir.
Thank you so much, Prakash sir. Actually, myself and Prakash Shetty sir, both were contemporary during our PG courses at MIT Manipal. Yes, I was doing my digital electronics and advanced communication in ENC department, and he was doing his M.Tech in biomedical engineering.
Thank you, sir. Thank you.
Thank you. Our association started in 2000-2001. Okay, thank you very much, sir. At the same time, my heartfelt thanks to Dr. Shantaram Rai, my good friend and also principal of AG Engineering College, and Mrs. Sahana Adyantaya. She gave a nice introduction and also welcome address. Our own PhD student and now head of the Department of ENC Engineering, your AJ College of Engineering, Dr. Jnani Shatapati, very dynamic and young professor, and all participants, welcome as well as very good morning. Okay, Prakash Shetty sir, am I audible? No?
Yeah, sir. You can continue. Yeah,
okay.
Very much audible.
Okay, thank you. Let us share the PPT now. Yeah, whether this PPT first slide is visible?
No, sir. You have to share, sir. You didn't share, I think.
1 minute. Yeah, it takes a little time. No, sir.
Yeah,
I have
it's
shared.
getting presented. Yeah, now it's like this.
Okay, sir. Thank you. The title of my today's talk is Machine Learning for Wireless Communication. And also the title of your FDP, it is recent trends in medical imaging and wireless communication. Actually, this machine learning is a recent trend in wireless communication. Although machine learning was popular in signal processing, especially pattern recognition or neural network, natural language processing, or Bayesian classification, or your biomedical signal processing. But machine learning concept is somewhat very much new to wireless communication area. Before starting, what is machine learning and what are the important applications of machine learning towards wireless communication? Let us brush up the fundamentals of this communication as well as the different hurdles that we have to face in this wireless communication. As you know, the communication is nothing but a transfer of information or a transfer of message from one place to another place, or one person to another person, or from source to sink. Communication engineering is nothing but transfer of information from one place to another place by means of modulation and demodulation technique that involves an extensive use of electromagnetic waves. So this is communication engineering or communication electronics. Communication is different, communication engineering is different, because in communication engineering that involves this modulation, demodulation, as well as this electromagnetic wave signal. Actually, the communication engineering or communication system is nothing but a power. And advanced electronics communication engineering in nowadays, it may win the critical war, or it may give the victory to the country if the country has very much sophisticated with the communication systems. That is the beauty of today's communication engineering. So the victory or the failure of a war, that depends upon the speed of communication. So also the communication is as essential as the food, energy, cloth, or anything. Without communication, there is no meaning for our life. Each and every living thing on this earth, they communicate with each other by different means. When child born, it starts crying. So it start crying. That is a form of communication. And if we have difficulty, we cry for God. So we communicate with the God. So one form or another form, all living things, they will communicate with each other. Communication is a very much essential thing for our modern human society. Communication, there are different types, you know, analog and digital communication, full duplex and simplex types of communication, wired and wireless type of communication. So different categories of communications are there. That is, depends upon the situation as well as application. Usually in communication, what we do is, according to this figure, the baseband signal that is shown at the left hand side of this slide is translated into passband by means of modulation. The modulation, it may be analog modulation or digital type of modulation. Usually the information signal or the message signal, it is analog in nature. It may be a text signal, this may be a voice, or it may be a music, or this may be a biomedical signals like EEG, ECG, or myo signal, or it may be a picture or video or any information signal. The baseband signal whose power spectral density, that means the power versus the frequency graph, you can see at the left side of this PPT. The spectrum is concentrated around 0 or DC. For text and speech signal, the bandwidth, which is around 10 to 20 kilohertz. If you go for picture, which is within a few megahertz. If you go for live video, it is around 5 megahertz. So depending upon the message type, the baseband bandwidth of the signal, that varies. As the bandwidth of baseband signal increases, then the modulated signal bandwidth also increases. That means picture needs more bandwidth than the speech signal or text signal. The live video, that needs more bandwidth when compared to your audio signal or text signal. Therefore, the important constraint for high data rate or high bandwidth signal is the spectrum. Okay, because spectrum or the bandwidth, it is very much costly and also precise, and each and every hertz, it costs a crores of rupees. In this modulation process, as I have said, the baseband signal is translated into bandpass signal by means of a modulation. For this, an auxiliary signal called carrier is used. According to the changes in carrier's phase, carrier frequency, and carrier amplitude, we have different types of modulations like amplitude, phase, as well as frequency modulations. In digital communication, these are the popular terms in analog communication. In the digital communication, it becomes amplitude shift keying, phase shift keying, as well as the frequency shift keying. In digital communication, this amplitude shift keying and phase shift keying, they combined in a hybrid fashion. We call it as a quadrature amplitude modulation. Why we have to go for modulation? Because if you make this baseband signal ride on a carrier, usually the carrier is a sinusoidal signal that carries this information for a very long, over a very long distance. Okay, the baseband signal in its crude or original form, that cannot travel through a large distance. So by means of modulation, by inserting a sinusoidal carrier, we can propagate these message signals over a very long distance. There are two types of communication category: wired and wireless communication. In wired communication, by using coaxial cables or by using this copper wire or optical fiber cable, you can directly transmit the baseband signal. No modulation is required. No modulation is required. But for wireless communication, this modulation or sinusoidal carrier is required, because only the sinusoidal signals, they can propagate in a wireless channel. Any other signal forms like square wave or triangular wave or any arbitrary waveform other than sinusoidal signal, they can't travel over a very long distance in a wireless media. This is because this wireless propagation is characterized by Maxwell's integral differential equations. The solution of integral differential equations that boils down to a form e power j omega t. The solution is e power j omega t. Only these EM waves in the form e power j omega t. That means either sine or cosine. They will survive in this wireless channel, and they can travel over a very large distance, and the loss of their energy is less when compared to other waveform shapes. Okay. Next, let us see the communication, how it has evolved over a very long history. Before the invention of these electronic signals and electronic devices, people used pigeon or some animals to carry the message. After, the smoke or fire were also used, and tribal people, they used the drums for communication, beating the drums. And next, the manual communication by means of a letter. You can see the postman. And next, Samuel Morse, he invented wired telegraphy. Actually, the communication started with wired and in a digital fashion. The wired telegraphy that uses a code called Morse code, that is dots and dash. Now the telegraphy is not there, and that entered to history. Then another important milestone in the history of communication is the invention of this analog telephone, wired telephone by Alexander Graham Bell, and next transition from analog to digital. So if you see these histories, very brief, Oersted, he invented the magnetic field in 1830 to 1840. Michael Faraday and others, they show the changing magnetic field that produces electric field, and also the invention of this generator. And Samuel Morse in 1838 demonstrated the telegraph, and 1876 Alexander Graham Bell, he invented wired telephone. And another important milestone in 1864, James C. Maxwell, he theoretically proved the existence of electromagnetic waves, but practical proof for existence of electromagnetic waves came only in 1887 by Hertz, by means of his very famous experiment called the spark gap or spark plug experiment. The invention of wireless transmission of signal that happened in 1895 by Marconi. He is treated as the father of this wireless. 1901, she succeeded to transmit the radio signals wirelessly over ocean, that between United Kingdom and Canada. Very important milestone that occurred in the history of electronics in 1904. That is Fleming, he invented the diode tube. It is not semiconductor diode, it is a tube that consists of anode and a cathode. In 1906, Day-4, he added one more terminal called plate to this diode tube. He called it as Audion. Okay, popularly it is called triode, but he called it as Audion. This is the first amplifying device that is used to amplify the audio. Therefore, Day-4, he called it as Audion. 1906, the AM broadcasting or the AM was invented, and 1920, the first AM radio station that was operated in Pittsburgh called KDKA. After that, the mechanical TV systems along with the electrical parts that was invented in between 1924 to 28. Many are claimed for the success of this TV invention, but John L. Baird from London is treated as father of the radio. And next, very important milestone that I have left here is 1918. That is Edwin Howard Armstrong. He invented super heterodyne receiver. The super heterodyne receiver is a very major receiver type in both analog as well as digital communication. Most of the world receivers like GSM phones or your the GPS or satellite communication receivers, TV receivers that form under that comes under this super heterodyne type. The same scientist Edwin Howard Armstrong, he invented FM, that is a frequency modulation, in 1933. Just you observe how the system or how the invention that gets complicated, or the definition of a communication engineering gets complicated from year by year. from simple to complex. There's movement from simple to complex invention. AM is the simplest type of modulation, but see in 1933, the invention of FM, it is a complicated analog type of modulation. And next, we can see 1937, the PCM, that is a pulse code modulation, the idea was invented. That idea was patented by Alec Reeves in England, but the PCM system, they came to operation during 1960s only. That is because of the bottlenecks in the technology. The matched filter, it was a very powerful receiver in the digital communication. It was invented by NORTH North in 1943. Kotelnikov, a PhD student in Russia, in 1947, he studied the signal space concept of digital modulation schemes by using a ground-Schmidt orthogonalization procedure. It is a very major step forward in the history of digital communication, so that in all the modern textbooks in the digital communication that adopt ground-Schmidt orthogonalization procedure to analyze the digital modulation performance schemes. And next, 1948, usually I call this year as a double Big Bang year. One Big Bang that happened in the area of electronics, and another Big Bang that commenced in the area of communication engineering. In electronics, the three eminent scientists, that is Breton, John Bardeen, and William Shockley, they invented the first germanium semiconductor transistor. They are working for Bell Laboratories. Although in 1906, DeForest invented Audion or triode, it was a wall, and it was the shape in the form of a semiconductor was given by these three scientists. They called it as a transistor, and invention of transistor. It is a big step in the history of both electronics and the communication, and also it shaped our modern technology in our civilized society. For this invention, they got Nobel in 1956. All the trio, they got the Nobel. And another Big Bang that happened in 1948 is the publication of a paper, a 92-page paper by Claude Shannon. He called it as a mathematical theory of communication. This Claude Shannon, he is regarded as the father of modern communication or digital communication. After publishing this paper, there is a lot of developments in both theoretical as well as practical happened in the area of modern wireless communication. And next, there is a big achievement in laying transatlantic telephone cable in 1956. 1959, Jacques Kilby, he was working for Fairchild Semiconductor. He invented first integrated circuit. For this, he got Nobel in the year 2000. Around 1960s, many error correcting codes were developed. The first error correcting code was invented by Richard W. Hamming in 1947. After that, Golay invented triple error correcting code. Around 1955, the convolution code as well as cyclic codes were invented. 1959, a powerful multiple error correcting code called Bose-Chaudhary and Hockingham code was invented. 1960, multiple as well as burst error correcting code. It's a non-binary code called Reed-Solomon code was invented by Irwin Reed and Gustav Solomon. And around 1967, Viterbi, he proposed a decoding algorithm called convolutional code. Decoding algorithm for convolution code, it is called maximum likelihood decoding, or it is called Viterbi algorithm. Actually, Viterbi algorithm is the fine tuning of the before known the Dijkstra algorithm, the shortest path algorithm. Usually the computer people, they knew this Dijkstra algorithm. So shortest finding, Viterbi he refined and he formed this Viterbi algorithm for convolution code decoding, and also this Viterbi algorithm used for equalizer design as well as different communication as well as other statistical problems. And also this is one of the most important algorithm that is used in machine learning. Okay, this Viterbi algorithm. And next, the T1 digital carrier system in a digital telephone it was installed by AT&T, that is American Telephone and Telegraph, in 1962. The optical fibers with the low loss was demonstrated in 1970. In 1971, the microprocessor was introduced by Intel, that is 4004. Then another important history is 1983, the 16-bit DSP processor. Because of DSP, because of microprocessor, microcontrollers, GPUs, and also high core or higher end this computer processors, the modern day high speed and also the machine learning aspects of communication is possible. Otherwise, without these advances in electronics engineering, there is no meaning for this communication. Okay, therefore I say electronics and communication, these two are the two faces of the same coin. One field which supports the progress of another field, so they have to go by hand in hand. Otherwise, by individually, there is no scope for each field. There is no scope for electronics without communication, or no scope for communication without electronics engineering. And 1985, there is a cellular mobile concept, or your mobile communication has started, but it was in the analog form that we will see later in detail. After that, the erbium doped fiber amplifier, that is an optical amplifier with the low loss, and flash memory in 1988 it was developed. And next, 2001, the wideband CDMA, that is a 3G, was invented. In between 1997, the LDPC code, that is a very big landmark in the history of error correcting code, was invented. 2006, the Polar code, another code, it's a competent for our 5G technology, was invented. So, like that, this electronics and communication, the development is going on day by day. It is a evergreen area. Now let us come to this wireless part, general communication part to the wireless part. In wireless, let us come to this mobile communication. The mobile communication, you can see the history can be classified in terms of 0G, 1G, 2G, 3G, 4G, 5G, and next upcoming 6G. The 0G and 1G, they are analog in nature. Actually, this 0G is just broadcasting. It's not mobile, or what you can say. It's not a mutual type of communication. It's a simplex. 0G is a simplex type of communication. For example, AM or FM or TV stations. It's just one-side communication. The broadcasting station, they transmit the information, and the receiving stations of the receiving units, they passively they have to receive whatever the information which is transmitted by the broadcasting stations. That is the meaning of simplex or broadcast. AM, FM, as well as VSB, that is vestigial sideband type of modulation, that is used in analog TV, are the examples for 0G as well as 0.5G. The 0.5G or half G, one important this one discrimination from 0G is the introduction of this FDMA, that is a frequency division multiple access. Multiple access means sharing the resources effectively. So FDMA, it's a type of analog types of multiplexing, but it can also be defined in the digital. We call it as YFDM now. So FDMA was first introduced in analog modulation systems. And next you come to 1G, around mid of 85, it was it's a high boom in the society of wireless communication, and this 1G is also called AMPS, AMPS. The AMPS means advanced mobile phone system. You see, each and every user in the place or locality is allotted a bandwidth of 30 kilohertz. Okay, this is very important. 30 kilohertz bandwidth is allocated. For AM, that is amplitude modulation, the transmitted signal occupies the bandwidth of 10 kilohertz. For FM, the transmitted signal occupies the bandwidth of 200 kilohertz. TV signal or video signal, that occupies the bandwidth of 5 megahertz. So, in the advanced mobile phone system, it uses analog modulation schemes and FDMA technology. 30 kilohertz is the bandwidth it is defined for each user. And at the end of this 1G, you can see the transition from analog modulation to digital. Here, the analog modulation is usually the SSB. Single sideband was used along with FDMA. Now let us come to the second generation. Second generation, the transition from analog modulation to digital modulation. This is called GSM. The second generation is also called GSM. That is a global system for mobile. Okay. And the modulation scheme used is GMSK, that is a Gaussian minimum shift keying. FDMA has ruled out a new digital multiple access technology called time division multiple access was introduced in the second generation, and you can see from 30 kilohertz channel bandwidth to 200 kilohertz channel bandwidth. Each and every user was allotted a bandwidth of 200 kilohertz in a cell. A cell concept or cellular concept, it was first introduced in 2G communication. Okay, and at the end of this 2G, that is next to come to this 2.5G, you can see the enhancement of a data rate. In the 2G, the data rate is around 13.4 kbps. Okay, 13.4 kbps. At the 2.5G, you can see the data rate is enhanced to 171.2 kbps. 13 kbps to 171.2 kbps, as well as instead of this GMSK, the pi/4 shifted DQPSK modulation is also introduced. In the GSM or 2G, only voice and this text message, it can be transmitted by using the technology. But during 2.5G, even picture can also be transmitted by means of the pi/4 shifted DQPSK as well as other equalizers techniques. And next, 2.75G, further improvement to this 2G, the edge, that is enhanced data rate for GSM evolution, 8 PSK, that is higher order modulation that carries more information. It is a bandwidth efficient scheme so that 384 kbps, see the increase in data rate, 171 kbps to 384 kbps within a bandwidth of a 200 kilohertz channel. The main aim of any communication engineer is to push as much as the data within a given bandwidth. For example, using BPSK, you can push 1 BPS data rate. 1 hertz, you can push just 1 BPS, 1 bits per second. By using a QPSK, that is slightly higher order modulation and compared to BPSK, you can push 2 BPS data within a 1 hertz bandwidth. Using 8 PSK, you can push 3 bits per second, 3 BPS data within a 1 hertz bandwidth. So as the modulation order increases, the data rate as well as the capacity of the channel you can increase, but at the same time the bit error rate increases. So this is the disadvantage, or it is a trade-off that we will see later. And next, the transition from this 2G to 3G. The 3G, the introduction of this CDMA, code division multiple access. Code division multiple access, it is different from a TDMA or FDMA technology. Actually, CDMA that takes the advantage of this spread spectrum technique. Spread spectrum technique, actually, it was developed for military communication during the Second World War. That is around 1943-1944. That time it was developed, and up to 1980s, this technology was hidden from the public. After 1980, the US government that has released this technology to the public so that the people started using it for commercial purpose. Instead of military, the people, they have started using for commercial purpose. That is nothing but your CDMA. WCDMA is a wideband CDMA. Actually, IS 856, that is interim standard 856, it is the standard defined for this WCDMA. Now you can see the 5 megahertz channel. The bandwidth defined is around 5 megahertz channel for each users, and the data rate increased to some 2 Mbps. See, from around 384 kbps to 2 Mbps. Okay, bandwidth is also increased. At the same time, the data rate is also increased. What are the advantages of a data rate? Increased in data rate, that by increasing the data rate, you can transmit the more sophisticated multimedia signal. Not only text or speech signal, you can transmit the picture, more precise picture. Further increase in the data rate, then you can transmit the live video. In that live video also, you can transmit 4K HD, 8K HD by increasing this data rate. For that, bandwidth enhancement or some other techniques are also required. Therefore, from one generation to another generation, you can see the enhancement of data rate. At the same time, the bandwidth is also stretched. But since the bandwidth is a very what you call limited resource, in order to save that, many technologies like compression and next MIMO or multiple antenna systems, multiple access systems, and next this one, in order to detect the signals in these dense constellation, this machine learning technique. All these things or technologies are evolved because of this bandwidth constraint as well as the need for high data rate. And 3.5G, it is called UMTS, Universal Mobile Telephone Services. So UMTS, it is a CDMA 2000, and also you can see the data speed up to 7.2 Mbps. Next, 3.9G around 2011. There's a LTE, a crude version of LTE, that is a long-term evolution with the 20 megahertz bandwidth that was introduced. And 4G, it was introduced in 2013 in the US and also Japan. 4G is called LTE. That's the introduction of another multiple access scheme called YFDM, that is orthogonal frequency division multiplexing. It is I can say it's a digital form of your frequency division multiplexing. And you can see it requires a bandwidth from 5 to 40 megahertz, depending upon the application. That is 5 to 40 megahertz, but you see the data rate 1 Gbps, very large or tremendous data rate, so that it can support the live video streaming, and also you can see the live TV programs. That is the beauty of this 4G. It's very popular, as well as it get a very good revenue in the telecommunication market. Now we are in the era of this 5G. Okay, actually 2020 it was released in most of the countries, but in India it has to be yet released. We are in a urge to this one. We are in a urge to deploy this 5G technology in our country. Recently, Ambani has announced by this October he will launch this 5G Geo phones. In 5G, actually the data rate assured is 10 Gbps to 100 Gbps. Along with the YFDM, the MIMO, that is a multi-input, multi-output, that is what you call multiple antenna systems are also introduced here along with the Almaty type of coding. And the multiple access is called SDMA, that is a space division multiple access. So in 1G it is FDMA, 2G TDMA, 3G CDMA, 4G YFDM, and in 5G I can say it's the SDMA, the space division multiple access or multiple antennas that are used. By seeing all these generations, the history as well as trends, I can say all even types of G are a mega hit or a success. 2G is a success, 4G is a success, but the odd Gs, that is the 3G and 5G, they have little failure. Therefore, people are now already thinking towards the 6G. What are the demerits in 5G? It should be rectified, and that problem should be addressed properly in the 6G. People are already talking about 6G and 5G and 6G. The major players are these machine learning techniques. Okay. Now these are the broad distinction between this 4G and 5G that adopts the machine learning. And you can see already I have told there's a tremendous improvement in the data rate as well as speed as well as the quality of service, all those things from 4G to 5G. And even the latency or delay is also reduced. In 4G, the processing speed, it takes a delay of 60 to 98 millisecond, and 5G it was reduced. It is within just 1 millisecond. The maximum mobility is limited to 350 kilometers per hour in 4G, and it is 500 kilometers per hour in 5G. Okay. Massive MIMO, it is the technology used in the 5G network, and simple multi-user or single user MIMO is the technology used in 4G technology. Okay. 16 antenna are supported in 5G. Only 2 antennas are supported in multi-user MIMO in 4G. So from one generation to another generation, you can see the increase in complexity of a technology also. Okay, increase in technology complexity, that needs very sophisticated type of algorithms as well as the competition. Therefore, it paved the way toward this machine learning. See the typical data rates that are required for different applications. The wireless sensor networks, it is less than 1 kbps, and some sophisticated may need up to 10 mbps. The speech communication, depending upon the quality of speech, 5 to 64 kbps is the data rate. Elementary data services, from 10 to 100 kbps. Communication between the computer peripherals, so 1 mbps data rate is required. Wireless LANs up to 100 mbps, and personal area networks, which is greater than 100 mbps, is the required data rate. Okay, if you go for very sophisticated as well as high quality video, then gbps of a data rate is also required. For all these communication, signal communication data transmission, we need this electromagnetic waves as a carrier. The different part of the spectrum, they are used as a carrier, starting from very low frequency to the extremely high frequency. Usually this very low frequency or low frequency, they are used for this maritime and submarine communications, and medium frequency, AM broadcasting and also maritime radio, it is used, and medium frequency, that lies between 300 kilohertz to 3 megahertz, and the what you call ground wave propagation, that is made possible for the distance distance traveling of these EM waves, and several hundred kilometers can be traversed by using this type of wave propagation. Another beautiful band in carrier frequency is the high frequency band, that lies between 3 megahertz to 30 megahertz. Actually, this wave propagates by means of a skywave propagation phenomena. These waves, they strike the ionosphere and reflected back, so that the very high distance can be traveled by using this type of high frequency waves. Even thousands of kilometers can be signals can be traveled. The amateur radio, or what you call this ham radio, the military communication shortwave radio, that operates in high frequency. Then very high frequency, line of sight propagation, ultra high frequency or super high frequency, extremely high frequency, millimeter waves, they are all line of sight of propagations, and the distance traveled by these waves without much energy loss is in terms of few kilometers to meters only, because this channel, wireless channel, that acts as a low pass filter. That means the channel doesn't attenuate low frequency signal, and high frequency signals are attenuated by this wireless channel greatly. Therefore, high frequency signals, these high frequency signals, they doesn't survive for a long distance in this wireless medium. Therefore, you can see AM radio, the signal transmits over hundreds of kilometers, but FM within just 100 kilometers. Okay, FM radio broadcasting from Mangalore, the station can be heard up to Kundapur, not more than that. Another repeater is required. So within just 100 kilometers, this line of sight propagation is possible. But in wireless communication, because of this data rate constraint, people have to go for this high frequencies. In low frequency, the bandwidth is low. It doesn't support megahertz or gigahertz bandwidth in this low frequency region. If you need very high bandwidth, then you have to go move towards very high frequency carrier. But attenuation is more. In the radar technology, that's also a type of wireless communication. I have not addressed any other types of communication like radar, sonar, or satellite, or TV, optical fiber communication. So many other types of communications are there, but yeah, that I have not addressed. Here, the radar, radio detection and ranging, especially during the Second World War, this radar technology was developed. Usually, that uses the frequency band from 1 gigahertz to 40 gigahertz. These bands are called microwave bands, and they are named with the specific letters L, S, C, X, Q, K, and K band. L for long, S for short, C for compromise, X for cross. KU means Kurz upper, K means Kurz, KATZ. Kurz is a German word and the meaning is short. Okay, the meaning of Kurz means short. KA means Kurz above. Kurz above, okay, Kurz above, Kurz and Kurz upper. These are the different terminologies adopted for radar during the Second World War. And also these bands not only defined for radar applications, GPS, wireless communication, mobile communication, UHF television, Bluetooth, and also your scientific experiments. For all those things, these bands are utilized. This slide or this paper cutting that I have taken it from Indian Express. It was a headline in March 1st in 2021, this year only. This slide that gives you the idea how precise the frequency or the bandwidth is. The auction or bid for this 4G spectrum that was happened in the end of February 2021, 700 megahertz, 800 megahertz, 900, 1800, 2100, and 2300, 2500 megahertz band. For all these bands, these are the frequency bands, and total bandwidth was 2.251 megahertz. That was kept for the auction or bid, and the bid amount was 3.92 lakh crores. It is not 3.92 lakh rupees, 3.92 lakh crores. 3.92 lakh crores is somewhat equivalent to the budget what India, which is dedicated to our defense, every year defense. So see the huge amount or the huge revenue that is coming from this spectrum. That is why utilization of the spectrum efficiently at the same time achieve more data rate. It is the evergreen challenge for any wireless communication engineer. Now let us see the digital or wireless communication. So there is a very minor or very hairline differences between this wireless communication and digital communication. There's a lot of difference between analog communication and digital communication. I think you are second year students. They have already learned analog communication and they are now learning digital communication. And higher semester people, they learn this wireless communication or mobile communication. What do you mean by first analog communication and digital communication? What are the differences? In analog communication, the baseband signal, that is a data signal, which is a text or speech or picture, which is analog in nature, or continuous in nature. In digital communication, this baseband signal, that is a picture or message or this voice signal or video signal, it is digitized. That means analog to digital conversion. That means sample, quantize, and coding. That is done. And this baseband signal then modulated by means of a analog carrier, that is sinusoidal signal, whose phase, frequency, or amplitude is changed in accordance with the message signal, with the results ASK, FSK, and PSK. That is digital communication. Okay, in digital communication, the baseband signal is discrete in nature. Analog communication, the message or baseband signal is analog or continuous in nature. Then what is the difference between this digital communication and wireless communication? Digital communication, it can be wired or wireless. In the baseband itself, if you can transmit over a wired channel like OFC or cable, then it is a wired digital communication where carrier is not required. If you make this baseband signal riding over a carrier signal, then it is suitable for wireless transmission. So that is nothing but wireless communication. In digital communication, we analyze the performance of a digital modulation and demodulation with respect to additive white Gaussian noise channel. Okay, the important or the main interferer for our digital modulation scheme is the additive white Gaussian noise. This is the only interference. But in wireless communication or mobile communication, not only simple additive white Gaussian noise, we will also take into account the different fading scenarios and also other interferences. The different fading channels like Rayleigh fading, Raysian fading, Nakagami fading, Gamma fading, or this one, Malaga fading, or this other type of scintillation effect, Doppler, all these adverse effects come in wireless communication. So this is a hairline difference between the digital communication as well as wireless communication. In digital communication, most of the time we analyze the signal with respect to the line of sight component. Okay, the transmitter and the receiver, they are in the vicinity of this line of sight. But in wireless communication, both the line of sight component as well as non-line of sight component we will take into account. In digital communication, we assume the channel is LTI, that is linear time invariant. That is AWGN is a linear time invariant channel. But in wireless communication, the channel is dynamic. It is non-linear as well as time invariant. Okay, it is time invariant. Now let us consider the blocks that often comes in digital or wireless communication. The upper one, it shows the transmitter side blocks, and the lower one, it is just the reverse of the upper. It comes in the receiver side. Okay, but in modern communication gadgets that have both transmitter and receiver in a single gadget. Okay, we call it as a transceiver. For example, your mobile phone, it is a transceiver. It consists of both the transmitter as well as a receiver. It can transmit the signal, it can receive the signal. In transmitter side, it's a digital communication. I'm not touching the analog communication, okay, because the machine learning applications are only defined for digital communication, not for analog. The information source, that is analog in nature, and it may be text, it may be picture, it may be voice, it may be a video, it may be music, anything. First, it is formatted. Format means analog to digital conversion, ADC, that is sampling, quantization, as well as coding. Sampling, which makes the time domain discrete, and quantization, it makes the y-axis or the amplitude discrete. Okay, amplitude is made discretized by using quantization. The time domain is made discretized by means of this sampling, and the round off is taken place in this coding. So that is the meaning of a format. This ADC or sampling process that makes the data redundant. That means the repetition. If redundancy is there, it requires more bandwidth. So already I have told, the bandwidth is very, very precise. The goal of any communication engineer is to push more and more data or increase the data rate, the first thing. Second one, utilize the spectrum or bandwidth properly. That means his goal is to increase the spectrum efficiency. How spectrum efficiency is defined? Spectrum efficiency is the ratio of data rate to the channel bandwidth. The unit is BPS per hertz. That is bits per second per hertz. So increase the spectrum efficiency or bandwidth efficiency. This is the second goal of the communication engineer. Third goal, increase the power efficiency. Power efficiency means enhance the life of the battery of a transceiver or mobile. Utilize less power and transmit the data or receive the data effectively, making very less error. So enhance the battery life, that is power efficiency. The fourth one is very important one. Reduce the bit error rate. While transmission over the channel, the bits get flipped. That is, 0 may be received as 1 or 1 may be received as 0. That phenomena we mathematically describe it as a bit error rate or the probability of a bit error. So reduce the bit error rate. That is the fourth important goal. And next one, the fifth one, reduce the cost and reduce the cost of the equipment. Make each and every user in the society, they can use the technology so that get the maximum benefit. That's the goal of every company. And also make the gadget user friendly so that each and every common person or uneducated person can use the device properly. From those goals only, from these goals only, our mobile phones, they are very much popular. They have reached even a very uneducated or very less educated people who lives in the village, very remote villages. So that's another important goal. What I have said is the sampling that introduces the redundancy. Redundancy that should be removed so that you can conserve the bandwidth. Therefore, that formatted bits that goes to the source encoder. The source encoder that does the compression. Actually, source encoder does the compression. This may be lossy compression or a lossless compression. ZIP, zip, that you know, it is a lossless compression. And TAR is also a lossless compression. And other type of compressions, whether MPEG or JPEG or Lumpal-Ziv or Shannon-Fano or this one. These are all examples for lossy compression. But it doesn't much reduce the quality of the information source. And the best thing is that reduces the bandwidth requirement. And next one is encryption. Encryption that comes under the cipher system that protects the data from spoofers, eavesdroppers, hackers. Okay, so authentication is defined in this encryption. There are different types of encryption standards are there, you know, that is advanced encryption standard or AES, digital encryption standards or DES, PGP or pretty good privacy, blowfish, quantum cryptography, elliptical cryptography, public cryptography. So many encryption algorithms are available. That is depending upon the application and also depending upon the resources for decrypt it. We have to wisely utilize these standards. And please note that all these types of flexibility, that source encoding, encryption, or next spreading or multiple axes, it's only defined for digital communication. These are all not possible in analog communication. Digital means flexibility. That is the beauty of digital communication. We can add more and more applications. We can just change the software by keeping the hardware itself. No need to change the hardware. But in analog communication, hardware has to change. But here in digital communication, no need to change the hardware. Only the program. We can just tweak the program and change or derive the required application. That is the beauty. And next block in this digital communication or wireless is a channel encoding. Channel encoding is nothing but error control coding. We call it as a forward error control coding. And also there is a reverse error control coding, or we call it as a ARQ that utilizes the feedback. What is the beauty of this channel coding? I think you people are studying in information and theory encoding that deals with this channel encoder. Okay, error control code. The name itself suggests the parity bits they are added at the encoder that combat against the channel noise. That combat against the channel noise, so that at the receiver and at the decoder you can correct the errors that made by the channel and you can get back the original message without error. Okay, so that is the beauty of channel encoding. There are so many channel codes like Hamming code, Golay code, Goppa code, Preparata code, Reed-Solomon code, BCH code, Polar codes, Turbo codes, LDPC codes. So many codes are available in forward error correction. And in the reverse or what we call the feedback type of error correcting mechanism. We call it as a ARQ, automatic repeat request. It's a terminology that is popular in computer networks. So there we have go back and selective repeat, stop and wait. This type of error correction or detection mechanisms are possible. And next one is multiplexing. In multiplexing and multiple access, just before the transmit antenna, you can see multiple access, the extreme end of this transmitter end. Okay, multiplexing and multiple access both sounds the same, but there is a very thin line of difference exists between multiplex and multiple access. Multiplex or multiple access in the broad sense that is used for effective resource sharing, that is bandwidth or power or any precise resources, precise communication resource sharing is nothing but multiplexing. In the multiplex, whether it's multiplexing or multiple access. Multiplexing actually that happens locally. The phenomena multiplexing that happens locally. The resource sharing effectively, it happens locally. That means the resources or different data from other sources like text data or picture data or voice data, all these sources are shared or they are made multiplexed within a PCB. That is called, we call it as a locally, okay, within PCB. If the sharing happens within a PCB or locally, that is multiplexing. If the sharing occurs remotely, it is called multiple access. That means in a satellite transponder, the different organizations or different countries or different channels belongs to different companies. You share the bandwidth. They share the bandwidth remotely. That is nothing but multiple access. There are different types of multiplexing or multiple access, starting from a frequency division, that is analog, but we can also define it for digital. Then the TDMA, it is digital, and CDMA, co-division multiple access, this is also digital. Polarization division multiple access, and space division multiple access. That is nothing but a multi-antenna system. So that is the new trend in the multiplexing technology. And next, the pulse modulation. Up to multiplexing, the informations are in the form of a bit. Bits, they are just abstract. We have to give some physical shape. Without giving any physical shape, we can't process it further, or we can't transmit it over a channel. The bits up to here, the bits, they are stored in the buffer, or the bits are stored in the random access memory. Okay, read on the random access memories. These bits should be given some shape, the waveform shape. That shape is given in a pulse modulation technique. It's a baseband only. Okay, it is baseband. For example, the line codes what you people are using, or industry that are using in the PCM, that's pulse code modulation, whether it is return to zero, non-return to zero, AMI, that is amplitude, alternate mark inversion, Manchester coding, all these line codes comes under this pulse modulation, as well as pulse position modulation, pulse width modulation, pulse duration modulation, all comes under this pulse modulation schemes. Again, it is a baseband modulation, not passband. You are not insulting the carrier. If you go for the wired communication, no need of this band pass modulation. You can just end here and transmit it over a cable. If you want to transmit the signal over a wireless channel, then you have to insert a carrier. A carrier is an dummy signal. Actually, basically, it doesn't bear any information. It is an auxiliary signal. According to the changes in amplitude, phase, or frequency, according to the changes in baseband signal, the amplitude, phase, or frequency of the carrier is changed accordingly, so that the bandpass modulation occurs. So that bandpass modulated signal can be transmitted over a channel. And next, if you need further protection against jammers or enemies, you can spread the signal, that is spread spectral communication. Here also there are different possibilities are there. There is direct sequence spread spectrum, frequency hopping spread spectrum, time hopping spread spectrum, hybrid of these. Okay. In between, in the recent years, this OFDM and MIMO that is also invented. OFDM is a potential candidate in 4G, and MIMO, usually the massive MIMO, is a potential candidate in a 5G communication. It's a multi-antenna system. These two are the added blocks in the recent wireless communication. The reverse operation happens in the receiver side, like frequency despread, demodulate, detect, demultiplexing, channel decode, decryption, channel decode, along with synchronization as well as equalization. Without synchronization or without equalizer, the communication, digital communication, is not what you call. It is what? The function is not ended without this synchronization as well as equalizers. Among these blocks, this modulation, this band pass modulation or pulse modulation, and here demodulation, here, yeah, demodulation and detection. Okay, modulation, and here demodulation and detection. These two blocks, modulation and demodulation, we call it as a modem. We call it as a brain of the digital communication system. And other blocks are called the muscles of the communication systems. Modulations and demodulations are very essential blocks. And some of the blocks may be optional. For example, encryption, channel encoder, or spreading, or multiplexing. They are the just optional blocks. You can, depending upon the application, you can just retain it or you can discard. As number of blocks increases, the complexity of the communication system also increases. Okay. Now let us go to next one. What are the different types of receivers in communication systems? Receivers are much more complicated, and also the design of receivers are interesting when compared to the transmitters. In the transmitter side, there is no much challenges when compared to the receiver side. At the transmitter side, we don't know what is the channel and what are the difficulties, we don't know. Just the information signal is sampled, then it is digitized, that is analog to digital conversion, then baseband modulation, passband modulate, and just you release it into the channel. But at the receiver side, it is not like that. When the transmitter signal travels through this complicated channel that introduces noise, interference, and all the disturbances, at the receiver side, the signal get deteriorated in such a way that its phase, amplitude, frequency, its strength, everything gets disturbed. From that very weak signal, the information has to be retrieved from this receiver. The receiver function is very much complicated as well as very much sophisticated. Therefore, in the communication engineering, the receiver design is much more challenging when compared to the transmitter design. There are two types of receivers in the history of our telecommunication. One is analog types of receiver, and another is a digital types of receiver. Actually, the digital type of receivers, they got inspiration from this, their predecessors, that is analog types of receivers. In analog types of receivers, there are three categories. One is a super heterodyne receiver, direct conversion receiver, and a low IF receiver. First one is the super heterodyne receiver. It evolved first, and next low IF receiver, and the next direct conversion receiver. And equivalent in the digital type, it is the first generation, second generation, and third generation digital receiver. We will see just briefly what is a super heterodyne receiver. Actually, in the super heterodyne receiver or this type of analog receiver, the blocks are analog. The blocks, they are analog in nature. That means the DSP or FPGA chip is not implemented in these types of receivers. Only the analog circuits like analog filters or analog amplifiers, analog detectors, or analog mixers, these circuits are utilized in this type of analog receivers. In the super heterodyne receiver, hetero means different, dyne means bit. The RF signal that is received from the antenna, which is RF signal brought into baseband signal in 2 or 3 intermediate steps. So this is the front end of the super heterodyne receiver antenna that catches the signal. Whatever may be the band of interest, that only is passed through this RF or radio frequency filter. Then the filtered signal, which is noisy, that is passed through the low noise amplifier. The weak signal gets amplified. Why? What is the meaning of low noise amplifier? Each and every electronic device or circuit, whether it may be amplifier, it may be oscillator, it may be mixer, it may be filter, it may be detector, anything that adds noise to the signal. That adds noise to the signal, because these are electronic devices. The electrons, they are random in motion because of thermal agitation that produces the random noise. That noise gets added to the noisy received signal. But in low noise amplifier, the design is in such a way that the noise gets added to the received signal is minimum. So that type of amplifier is called low noise amplifier, that boosts the weak incoming signal, because you may transmit the signal from your end in terms of watts, kilowatts, or megawatts of power, but at a distant receiver, which is 100 kilometers or 1000 kilometers away, that 1000-watt signal may come around 1 nanowatt or 1 picowatt. That much of weakened signal is experienced at the receiver antenna, that must be boosted for further processing. So low noise amplifier. Then image rejection filter, because the unwanted signal that is far away from the wanted signal that acts as an image that should be rejected, that is a tuned filter along with the local oscillator. This local oscillator, it converts RF signal into intermediate frequency signal. For example, your FM radio, the frequency band of interest is 88 to 108 megahertz. That is the carrier frequency, and intermediate frequency is 10.7 megahertz. So that 88 to 108 megahertz is bring down to 10.7 megahertz by using this local oscillator. This local oscillator frequency, sometimes it may be greater than the incoming RF signal frequency, or in some receivers, this local oscillator frequency may be less than the incoming RF signal frequency. If the local oscillator frequency is higher than the incoming RF signal frequency, it is called high side injection. If the local oscillator frequency is less than the incoming RF signal frequency, then we call it as a low side injection. Okay. Here the name heterodyne. Hetero means different, dyne means beat or mix. The incoming RF signal frequency and local oscillator frequency, they are different. They are hetero, and they are mixed together to get the intermediate frequency. So the name is called heterodyne. And also it is super, because the intermediate frequency, which is above the supersonic frequency. Supersonic frequency is above 20 kilohertz. Okay, that non-audible frequencies are called supersonic or ultrasonic frequency. This terminology has derived during the First World War. Therefore, same name is written, super heterodyne. The intermediate frequency is above the audio range. Therefore, it is called super heterodyne. Intermediate frequency is above that. Next, the noise is further filtered by using this IFF filter. From IF filter, the intermediate frequency, see the spectrum in the frequency domain. The RF signal, whose carrier frequency is around 1 megahertz, after beating with the local oscillator, it RF signal brings further reduced in its frequency and bring it around the intermediate frequency, 10.7 megahertz for FM, 455 megahertz for AM, around 40.5 megahertz for radar, 70 megahertz for satellite. These are the different intermediate frequency depending upon the application. And IF filter, that goes to the variable gain amplifier, or it is also called AGC. Actually, AGC, depending upon the detector requirement, the detector, it may be analog detector or discriminator, it may be coherent or non-coherent. Depending upon the threshold requirement of the detector, the AGC or VGA, which reduces or increases the IF signal strength. So, and then the detector, it gives the baseband signal, that is AF, that is audio frequency. Okay, that is the super heterogeneous. All the components are analog in nature. These are the early radios that works on the principle of this super heterodyne. You can see the size as well as the complicated circuitry that utilizes this analog filters, analog mixers. They are made up of these coils as well as so many resistors and crystals. Okay, and these are some walkie-talkies also. The walkie-talkies are examples for half duplex systems. Okay, and the next one is low IF receiver. The just before going to the this one, zero IF receiver, let's see what is a low IF receiver. In the super heterodyne case, the IF frequency is almost midway between the RF frequency and the baseband frequency. But in the low IF frequency, the intermediate frequency is very near to the baseband frequency, but it is not around 0 hertz. Baseband frequency is around DC or 0 hertz, but in low IF receiver, the IF frequency is just 1 or 2 bandwidth, 1 or 2 channel bandwidths away from this DC frequency or 0 hertz. These low IF receivers, for example, whether GSM phones or wireless LANs, your Bluetooth or GPS, that works upon the principle of low IF. The beauty of this low IF is DC offset problem as well as the yellow leakage. That is the common problems in the zero IF receiver. That two problems, they are overcome in this low IF receiver. For example, in Bluetooth, the RF frequency is 2.482 gigahertz. Okay, the Bluetooth that operates with the RF or carrier frequency of 2.482 gigahertz, that comes in the ISM band, that is industry, scientific, and medicine band. In the low IF, the IF frequency is 1 megahertz or 2 megahertz. It is not 800 megahertz or some 100 megahertz like that. It is 1 megahertz or 2 megahertz is the IF frequency. Super heterodyne, it should be around 800 megahertz or 100 megahertz, in that range. But here it is 1 megahertz or 2 megahertz. That is the meaning of a low IF receiver. Okay. And next, the direct conversion receiver or a zero IF receiver. That is now the trend is here. The RF signal, that is in terms of gigahertz frequency, the carrier frequency is a gigahertz. At a one shot, it gets converted into baseband signal. There is no intermediate frequency conversion. There is no concept of IF. So that the image frequency, that problem is resolved by using direct conversion receiver. But the two important challenges here, one is IQ imbalance, the DC offset, and the phase noise. These are the challenges, but by using sophisticated DSP or FPGA baseband software techniques, we can mitigate those problems. The trend is a direct conversion receiver now. Okay, the software defined radios that operates on the principle of this direct conversion receiver. So you can see the block diagram here for the direct conversion or zero IF, or what you call say just homodyne. Another name for this is a homodyne receiver, because this incoming signal frequency or carrier frequency and local oscillator frequency, both are same. If it is 1 gigahertz, the local oscillator frequency is also 1 gigahertz. But in case of super heterodyne or low IF, this frequency, that is the incoming antenna, and local oscillator frequency, both are different, hetero. But in direct conversion, both are same. It is a homodyne receiver. RF filter that just filters the required band, that allows through this filter. Low noise amplifier that boosts the strength of the incoming weak signal. Local oscillator that produces the same frequency as that of RF or carrier signal. At one shot, this RF band is converted into the baseband signal, and other high frequency signal because of this beating is filtered out by means of low pass filter, and this baseband signal is further processed, and the data is recorded by using detector as well as a demodulator. Okay. Now let us come to very briefly the structure of a modern day digital receiver. There is no much difference between the analog receivers as well as a receiver, this one, digital receiver terminology as well as technology. Actually, these digital receivers, they gained the knowledge as well as their operations principles from the analog receiver type. There are three types of digital receivers according to how they evolved in the history. One is the first generation, second is the second generation, and the last one is the third generation digital receiver. The first generation digital receiver is the architecture or principle is somewhat similar to the super heterogeneous receiver. The second generation digital receiver, its operation is similar to the low IF receiver, and the third generation digital receiver, its operation is similar to the zero IF or direct conversion or a homodyne type of analog receiver. Let us come first this discrete time detector or first generation digital receiver. The front end of the receiver is same as that of the analog, that is antenna, then RF filter, low noise amplifier, and next local oscillator, mixer, after that IF signal. Okay, up to here the operation is same. Once the signal analog signal gets converted into IF, you see there are two types of markings here, one full white and another one is shaded. The shaded, that shaded blocks that represents the discrete time signal processing, unshaded that gives the knowledge of this analog signal processing. Okay, that represents the analog signal processing. IF signal from the mixing, that is analog in nature, that IF signal further bring down to the baseband by means of analog IQ signal that is obtained from voltage control oscillator. Voltage control oscillator frequency is dictated by means of carrier phase this one phase lock loop, whose operation is controlled by this DSP. These are all the discrete block. According to the frequency that has to be produced to detect the signal at the receiver, DSP dictates the carrier phase PLL, and with this carrier phase PLL that is discrete in nature, which output goes to the digital to analog converter, because VCO is analog in nature. The VCO frequency changes according to the carrier phase PLL dictation. And VCO that produces two signals, one is I and another is Q. I signal is nothing but in phase, that is cosine. The Q signal is quadrature, that is nothing but sine. The sine and cosine signal, which is weighted with IF signal, IF is converted into the baseband signal. The baseband signal is passed through this low pass filter, and low pass filter that removes the aliasing components, and these aliasing components are removed, and then this analog signal or analog baseband signal gets converted into digital by means of ADC, analog to digital converter. Actually, ADC and DAC comes under mixed signal processing. Okay, it is comes under mixed signal processing. These are analog signals, and here the signal undergo discrete time signal processing or digital, and in between the interface is a mixed one. Okay, and the sample rate of ADC is decided by symbol timing synchronization, and symbol timing synchronization, for that the PLL is used. This PLL, it operates on one of the principles like early late gate or Mueller and Mueller, or this one Gardner algorithm. So this dictates the sample rate of this ADC. This discrete samples from ADC comes to the matched filter. The matched filter actually it decides matched filter that gives the outputs in terms of zeros and ones, and the detection of zeros and ones is happened in the DSP or FPGA block with the which is compared with the known threshold, and according to the threshold value, the output bit is decided as 0 and 1, and that gets output from the DSP blocks. And 0 and 1s again they have to reconstruct according to the ASCII or according to the compression format. After that, that should goes to the display, or that should goes to the this one CRT, that is the cathode ray tube or LCD screen, or that should go to the speaker. Okay, here you can see equal number of analog blocks as well as some equal number of discrete blocks in first generation. In second generation, I think the screen is visible to you all. In second generation, you see the placement of this ADC. First generation, the ADC is placed after baseband. In second generation digital receiver, the analog to digital converter is placed just after the IF signal. So how you are placing this ADC, that decides the generation of these receivers. This second generation is somewhat equivalent to the low IF receiver. It is, and we have already seen in the analog type of receiver. IF signal directly is fed to the ADC. The sample rate of ADC is decided by this symbol timing PLL or symbol time synchronization block. Actually, it is controlled by this DSP. See the role of a DSP. Actually, the multi-rate signal processing and adaptive filters. These two are the very important concepts that play a major role in these types of modern wireless communication. Because of this discretization, because of the sample what we are getting, we can process it through the simple ML or MAP type of old technique, or nowadays the data rate is also high, the bandwidth is high, because of high data available, we have to go for the machine learning technique. The ordinary or what we are using before, the ML or MAP, they fails to handle this enormous data. Therefore, the ML technique or machine learning technique that comes into rescue the successful recovery of the information. So that all happens because of a discretization of your receiver by adopting these DSP techniques. Okay, ADC and analog to digital conversion. The sample rate is reduced by means of this DDS or direct digital synthesizers. The direct digital synthesizers, it is equivalent to the frequency synthesizers in the frequency domain. The frequency of DDS or direct digital synthesizer is controlled by means of discrete carrier phase PLL. We call it as a NCO, okay, numerical controlled oscillator. Yeah, PLL is a terminology that is used in analog communication, but numerical control oscillator, it is the terminology used in discrete time or digital domain. According to this DDS frequency, the baseband signal conversion as well as the correction of incoming signal phase as well as the frequency offset had done, and then it goes to the resampling filter. Resampling filter is a decimation filter. Already these are all multi-rate filters, because ADC operates in one sampling rate, and data rate it operates in another sampling rate, and in between different frequency or sampling rates are there. Therefore, we have to go for the different sampling rate or multi-rate sampling type of techniques. It is a multi-rate resampling filter or a low-pass filter that removes the spectrum folding as well as that removes the aliasing components, and then it goes to the matched filter. Matched filter, again, it's fed with the equalizer. Equalizer actually that removes the ISI, that is intersymbol interference components, and it cleans the signal. The equalizer operation is dictated by the training sequence or the pilot sequence, and these 0 or 1 from the match filter that further processed in the DSP to remove the compression as well as forming the frames as well as reconstructing the ASCII symbols or this audio signal reconstruction, everything, and output it goes to the respective transducer. And next one is the last type or the modern type of this one receiver, that is the third generation digital receiver. Here you see the ADC is placed just after the RF signal. The RF signal, where you are getting RF signal, antenna, after that RF filter, after that low noise amplifier. After this low noise amplifier, there is no IF conversion. The LNA output is given to the ADC. So the requirement here is very high speed ADC requirement, because nowadays the RF signal whose frequency is in terms of gigahertz. If you go for millimeter wave, it may be 40 or 60 gigahertz. Therefore, ADC should operate 3-4 times more than that frequency. Okay, so gigasamples per second is the operational speed of this ADC. This is a challenge. Okay, for modern technology, designing a high rate, very high resolution ADC and DAC, they are challenged. This and research is going on continuously, as well as this ADC and DAC for high data rate or high sampling rate is very much costly. So because of this bottleneck, this type of receivers are not much popular, but advances in technology in the future, all the receivers may be replaced with this third generation. Only some sophisticated higher end software defined radios that operates on this third generation type of a digital receiver. Okay, the ADC sample or the discrete samples that goes to the resampling filter, its operation is controlled by symbol timing PLL. Then the samples comes to the CORDIC, that is coordinate rotation digital computer. Actually, it is a signal constellation rotation technique, so that the disturbed constellation because of noise is restored by means of this CORDIC. Very, very important as well as beautiful algorithm. The explanation and implementation of the CORDIC, it may take one full day. So lot of things are there in this discrete type of communication. And restored constellation points or this one fed to the matched filter, the decision will come 0 and 1. They are just what you call decided depending upon the threshold and like that. Next, let us come to the goal of a communication engineer. As I have said, it's a very important graph that you can often see in wireless communication or digital communication. It's a bit error rate versus EB by N0 or simply SNR. EB means energy per bit, N0 is a single-sided power spectral density of additive white Gaussian noise. This is a curve. Actually, it is plotted for BPSK, binary phase shift keying, for over AWGN channel. It is called waterfall type of curve. Increase in EB by N0, that decreases the bit error probability, and decrease in EB by N0, it increases the bit error rate. But according to Shannon, he said that without increasing EB by N0, by utilization of error control coding technique, you can decrease the bit error rate, and also you can push this bit error rate curve towards my limit. That its limit is called Shannon limit, that is minus 1.6 dB. According to him, no need to utilize 9.6 dB to obtain 10⁻⁵ bit error rate for a BPSK. You can just utilize minus 1.6 dB of EB by N0 or SNR along with some error control coding, so that even for minus 1.6 dB, you can achieve a bit error probability of 10⁻⁵. What do you mean by the bit error probability of 10⁻⁵? Suppose, just think, you are going to transmit a 10⁵ bits, that is 1 lakh bits from Mangalore to Surathkal. In between, the channel is assumed as a AWGN channel. I receive 1 lakh bits. Out of 1 lakh bits, 1 bit goes in error. Instead of 0, I made detection as 1. 0 is detected as 1. All 99,999 bits are detected correctly. Only 1 bit goes in error. Then bit error probability is 1 by 10⁵ or it is 10⁻⁵. Okay, that is the meaning. So instead of BPSK or MRE, quadrature amplitude modulation, we can go for MRE FSK. It is a very interesting type of digital modulation schemes, that is frequency shift key. The beauty here is, as M increases, that is the number of levels in this digital modulation scheme increases, you can see the bitter rate decreases, or the energy efficiency, the power efficiency increases. For binary FSK, it is the red one. And the next, for 4-ary FSK, you can see the bitter probability is here, the curve. M is equal to 8. 8-ary FSK, the green one. As you increase the level of modulation in the FSK, the bitter rate decreases, or the power efficiency increases. You can save the battery power. But the main disadvantage of MRE FSK scheme is it increases the bandwidth. It increases the bandwidth. For us, bandwidth is more precise than power. At a current scenario, the bandwidth is more precise than power. Okay. Therefore, people are looking for more bandwidth efficient schemes rather than energy or power efficient schemes. And also, these MRE FSK schemes, their detection as a M number, that is 4-ary, 8-ary, 16, 32-ary, as the number of level increases, the complication, while detection as well as demodulation also increases. Therefore, people will look for this PSK or QAM type of schemes. Now let us see the BPSK. It is a signal constellation diagram, and the effect of AWGN, that is additive white Gaussian noise, on this BPSK scheme. For 12 dB SNR or EB by N0, this is the disturbed constellation. If you increase the power, or if you increase the SNR, then you can see the effect of noise also gets reduced. Then let us go for a higher order modulation. This is the higher order modulation, that is a QPSK. QPSK, it is a two-dimensional signal constellation. You have both I and Q. In BPSK, it is one-dimensional. Only one carrier is sufficient to carry the information signal. But in case of a QPSK, two orthogonal carriers, sine and cosine, are used to carry the information signal. In the QPSK, you can see there are 4 constellation points or symbols, S1, S2, S3, S4. There are 4 symbols, and one symbol is nothing but 2 bits. Okay, one symbol is 2 bits, so it is more bandwidth efficient than BPSK. But the disadvantage is, as the signal becomes dense, but in QPSK, its bitter rate performance is equivalent to the BPSK. But if you go for 8 PSK or 16 PSK, for example, next I will show you, the signal constellation becomes more and more dense, the bitter rate also increases, but bandwidth efficiency is more if you go for higher. See, this is the bitter rate performance for different MRE PSK schemes. M is equal to 2, it is BPSK, M is equal to 4, QPSK. BPSK and QPSK, their bitter rate performance is same, because QPSK, it uses 2 carriers that are orthogonal to each other. Because of that orthogonality advantage, bitter rate is same. For example, in order to obtain a bitter rate of 10 power minus 5, both PSK and QPSK, that utilizes 9.6 dB of EB by N0, precisely 9.6 dB. If you go for 8 PSK, it is more bandwidth efficient, but it is not power efficient, because bitter rate of 8 PSK is more than BPSK or QPSK. That means after 8, next 16 or 32 or 64 are a PSK, these curves, waterfalling curves, they are moving away from this channel limit. Channel limit is minus 1.6 dB. They are moving away from this channel limit, or they are moving towards the right hand side. So they are not bandwidth efficient. If the curve, if the shift towards left, or if it is coming towards the channel limit, then we can say that they are power efficient. Okay, they are power efficient. But here they are not power efficient. Bitter rate degrades, but they are bandwidth efficient or spectrum efficient, because in the 64 or a PSK, within 1 hertz bandwidth, you can push 6 bits per second. Okay, you can push 6 bits per second. In 32 or a PSK, within 1 hertz bandwidth, you can push 5 bits per second. That is the beauty. By utilizing error control coding, like Hamming codes or BCH or Bole codes, or next we'll see the convolutional codes. What it can do is you can increase the power efficiency, or you can push the left hand side bit rate curve towards the right hand side, or towards the Shannon's limit. That is the beauty of this error control coding. As the length of the error correcting code increases, for example, 127,64 binary, Bose-Chaudhary Hockingham code with error correcting capability of 10. It's a very complicated code. By utilizing this, you can achieve the power efficiency, but at the same time, the complexity as well as the increase in the bandwidth, or stretching the bandwidth, or penalty in the bandwidth also occurs, because error control coding is not a bandwidth efficient scheme. In order to get error detection and correction, you have to add extra bits called parity bits. Parity bits, they are just dummy bits. They need more bandwidth. Okay, they need more bandwidth. And this is convolution code. There are two types of codes. One is a block code and another is a convolution code. The previous slide, it shows the performance of block codes. Here, the convolution codes. Block codes, they are used in usually the this one data storage applications like CD, DVD, or pen drives, hard disk drives, where the slight delay is tolerable. In convolution codes, here the encoding and decoding is instant for real-time applications like your GSM phones or satellite communications, or all these types of applications, real-time applications, where delay is not tolerable, where these convolution codes are used. And better than convolution or block codes is the LDPC, turbo, or polar codes, and these codes are called Shannon limit approaching codes. Here you are seeing a bit rate performance of a low density parity check code that comes under this block code, and you see the length of this low density parity check code, that is 2 lakhs 2,12,000. It is the length of the code, and length of the message is 1,02,83. Such an enormous block length, and rate is half, that is k divided by n. That is nothing but message length divided by encoded bit length. That is known as a code rate. The code rate is half. It's an enormous length. For this type of LDPC or low density parity check code, usually the traditional method that adopts two types of algorithm to decode it. One is called bit flipping algorithm, and another one is sum product algorithm or message passing algorithm. Actually, it's a message passing algorithm that comes under the soft decision decoding or iterative decoding. Actually, it takes a lot of iteration to decode such a type of very long code length. It involves a latency and as well as so much computational complexity. We can replace that message passing algorithm or belief propagation algorithms by using this machine learning technique, that is either deep neural network or convolutional neural network. Once we train the bit node as well as parity check node to handle this type of data, lot of computation complexity, time, everything can be saved. So the machine learning will rescue for this type of very large length codes. These are all with respect to the AWGN or a simple LTI channel, linear time invariant channel. But in wireless communication or mobile communication, in that case, the transmitter is moving, the receiver is moving, or sometimes both are moving at the same time. In between transmitter and receiver, this is a transmitter base station, this is the receiver mobile phone. In between, so many obstructions in the form of man-made or the nature-made. You can see nature-made, it may be trees, hills, forest, or the man-made, the buildings or apartments, flats, lamp posts. Therefore, always you don't get a line of sight path from transmitter to the receiver. At the same time, at the receiver, you will get the non-line of sight components by means of reflection, refraction, diffraction, scattering. So they will arrive to the receiver with different delay, with different phase. that phenomena collectively called fading, and fading is usually it is a time variant, and also if Doppler gets added because of the mutual traveling of transmitter and receiver, the system becomes non-linear also. The system becomes non-linear. So handling non-linear and time variant, is very, very difficult when compared to LTI system. In most of our engineering studies, we analyze the system by assuming it is LTI, that is linear time invariant. If I first define as a teacher or a student, if you define, let us consider the system is LTI, the life is made simple. Okay, both faculty as well as students, the life is made simple by assuming simple LTI. If it is non-linear as well as a time variant, then it is a nightmare. Lot of competitions as well as a lot of complexity is involved. But a real life scenario is always, it is dynamic, that is non-linear as well as time variant. So this is the such a type of scenario. Therefore, this fading, AWGN is this scenario. The AWGN is additive in nature, but the fading, you can say it is a multiplicative in nature. Therefore, the seriousness or severity of a fading on signal is more in compared to this AWGN. Okay, because of this complicated fading when compared to AWGN, the bit error rate for fading channel is much more when compared to the AWGN channel. You just see this graph. The rightmost graph, so that is a linear fall of bit error rate by increasing EB by N naught. That is for a fading channel, which is a Rayleigh fading. There are different types of fading, I have said. Rayleigh, Raytheon, and Nakagami. These three are very popular. In the Rayleigh fading channel, actually, there is no line of sight component or specular component is available at the receiver. Okay, all signals that gets reflected, refracted, scattered, or diffracted and arrive to the receiver in different time with different delay, and also if Doppler is the different frequency. Okay, so that type of situation is the Rayleigh fading. In the Raytheon fading, along with the line of sight, non-line of sight components, some significant line of sight components also arrive to the receiver. That is the Raytheon. Both Raytheon as well as Rayleigh along with AWGN can be characterized by using a Nakagami type of fading model. All these are the PDF. Okay, all these are PDF, that is probability density functions, because all these fading phenomena are random. They are not deterministic. All random phenomena can be explained by means of random variables, probability, and random processes. In that, this mean, variance, kurtosis, autocorrelation, post-spectral density, autocovariance, and all these things are ergodicity, or this one, sample mean, or the terminology used to analyze those types of parameters. And these parameters, all the set parameters, along with coherence time, Doppler frequency, and level crossing rate. These are the peculiar terminology that is used in fading. All these terms, they are used in machine learning, especially deep neural network or convolutional neural network, to train the hidden layer. Depending upon the number of these parameters available, what we call it as a degree of freedom. Now, upon that, the number of hidden layers is decided. And these hidden layers are used to train the neural network, so that a particular pattern of signal is arrived at the this machine learning block or this deep neural network block. Then that classifies, yes, this channel is belong to the Rayleigh fading channel, or this belongs to the Raytheon fading channel. So that type of characterization is possible. According to this graph, you can see here, although you are increasing EB by N naught like anything for fading channel, the fall of this bit error rate is linear. It is not an exponential fall or a waterfall. You can observe this waterfall in case of AWGN. Just a slight increase in AB by N naught for AWGN, there is a drastic fall in the bit error rate. But here you can't observe that sudden or drastic fall of BER in case of this fading channel. Okay, so that shows you the severity of fading effects on this data transmission over the fading channels. Okay. In between, actually, I had a plan to show you the Simulink simulation of all these digital communication, bit rate, I diagram, as well as a constellation diagram for AWGN as well as a fading channel. But already time is 11:45. Now there's an urge for me to wind up. Therefore, if time permits or if any in the next future context, I can explain all this by means of Simulink. So sorry for that. Okay, next. Let us at last we come to a very little part on this machine learning or this what you call the artificial intelligence aspects of this wireless communication. Actually, this machine learning it is a sub part of artificial intelligence. As I have already mentioned during my initial lecture slide, deep learning is not a stranger for signal processing engineer. They are using before or they are using many years before for speech synthesis, speech recognition, pattern recognition, image processing, natural language processing, artificial intelligence, fuzzy genetic algorithm, molecular communication, okay, detection and estimation, so many aspects. Only the application for deep learning for wireless is somewhat new. It is because of the need of processing a large data in this 5G, 6G communication era or big data analytics. Only that giga samples per second or gigabits per second, that much of enormous data can be handled by only using this type of deep learning or machine learning techniques. Otherwise, the traditional MAP or that is maximum a posteriori or ML, that is maximum likelihood, or some traditional methods like hypothesis testing or log likelihood ratio, all this will fail for these types of data. Then what do you mean by this machine learning? Machine learning, which refers to the design of computer algorithms for gaining new knowledge or improving existing knowledge and making predictions or decisions based on empirical data. Okay, that is the meaning of machine learning. There are three types of machine learning, or broadly classified, you can classify it into three types. The first one is supervised learning, second one is unsupervised learning, and the third one is reinforcement learning. Okay, supervised learning, unsupervised learning, and reinforcement learning. These are the three types. In supervised learning, it is just like learning the concept from a teacher. That means some known sequence or pilot sequence, they are transmitted along with the signal. According to the known sequence, how it gets deteriorated or interfere, based upon that knowledge, the actual data signal is analyzed and detected according to this supervised learning. In unsupervised learning, the pilot or known data sequence is not transmitted. Just whatever data received, and by extracting the statistical features like mean, variance, or autocovariance, or kurtosis, and taking the log likelihood ratios and study it and try to detect which symbol or which bit was transmitted. That is nothing but unsupervised learning. In the supervised learning, the technologies like Bayesian classification, support vector machines, hidden Markov models, principal component analysis, EM, that is expectation maximization algorithm. These are the very popular techniques. In unsupervised learning, actually it deals with the clustering. For example, KNN, K means near neighbor types of clustering. All these clustering types of algorithms that comes under unsupervised learning. In the reinforced type of learning that comes in between supervised and unsupervised, it's the dynamic type of machine learning techniques. Actually, the data analysis as well as this data classification, everything is made dynamically by extracting the features of the signals or data on spot. That comes, reinforcement learning comes in between both unsupervised and supervised type of learning. Here, this deep neural network skeleton is given. One is input layer and output layer. In between, the hidden layer is operated by means of a bias. The bias and also the weight is assigned for different input samples, and these weights, they may be fixed or adaptive depending upon the application as well as the competition and complexity. Actually, you can see the bias, it is a mathematical function. They are non-linear. The different bias functions are given in the table. The sigmoid or tan H function, softmax function, or ReLU, that is nothing but rectified linear units. They are all non-linear. Because of this non-linear function, you can get a very successful result in this deep learning or machine learning techniques. So this is a neural network that is used for this machine learning, input layer and output layer. In between, so many hidden layers. The number of hidden layers, it depends upon the number of features, okay, number of feature vectors, or degree of freedom. How many feature vectors you can extract from data, that decides the number of layers in the hidden layer. Okay, number of increase in hidden layer, that increases the precision of the result. At the same time, computation complexity as well as the delay also increases. But the beauty is, once the neural network is trained properly, then there is no difficulty. Then you get the output without any delay or latency. What are the features? The features may be the statistical terms like mean, variance, autocovariance, autocorrelation, skewness, kurtosis, Doppler shift, or level crossing rate, or this one, what you call delay spread. All these are the features. Next, the last 2-3 slides that gives you a very brief applications of machine learning in wireless communication. In the military communication, it is required to analyze and detect the enemy's communication signal and also see which modulation that enemy has used, whether it is analog modulation or digital modulation. In case of it is analog modulation, whether it is a AM or FM type, or in AM, what are the different categories. If it is digital modulation, whether it is PSK type, FSK or ASK type, all this can be analyzed, as well as the modulation types can be detected by using this machine learning technique. Between input layer and output layer, there are different hidden layers. Here only 2 layers are shown with the different activation functions like sigmoid or linear activation functions are used. From that, the cyclostationary and ergodicity property of these modulated signals are analyzed. Very less features are sufficient to decide whether it is AM, DSP, LSP, or USB, or FM or PSK. Along with these features, one more key features, because depending upon the modulation, like I say, one more feature is required to decide the signal is binary ASK or 4-array ASK, and extra feature is required to detect whether it is a binary FSK or 4-array FSK. That means detection of MRE ASK or MRE FSK is not as easy as that of AM or PSK technique. Okay, so one can take it as a research or good project for the further study, automatic detection of modulation. And next one is channel decoding. Here is the block diagram that shows the channel decoding of a LDPC by using neural network. Actually, Bayes propagation is used to, it is a iterative decoding. You can see the feedback between the 2 layers. One is odd layer and even layer. Actually, odd layer, it represents the bit node, and even layer represents the parity node, and number of iterations between these 2 layers or these 2 nodes that decides the quality of the output. So it is by using these hidden layers and LLRs, circulating the LLRs in between these two layers, that strengthen the detection. And the last one, MIMO, that is multi-input and multi-output detection, that comes under SDMA, that is a phase division multiple axis, that is adopted in 4G, 5G, and all next coming G. The MIMO is one of the important components. In MIMO detection, the detection process, the detection of the symbols or the information of the receiver, that mainly depends upon the correct estimation of the channel. Actually, channel estimation that takes you to the formation of channel matrix. The channel matrix is called here the H matrix. H matrix or channel matrix, the matrix that is defined between this, the mathematical structure that is defined between the transmitter and receiver, depending upon the signal quality and depending upon the fading. Actually, how the signal strength get boosted or how the signal strength get attenuated, both in amplitude and phase. That is described by this channel matrix, just like your impulse response. If it is a single vector or a single input, single output channel, we call it as the impulse response. For multiple input and multiple output, or multiple transmit antenna and multiple receive antenna, we have to go for, instead of a simple scalar or simple vector, we have to go for a matrix, that is a channel matrix. The channel matrix, the difference between the transmitter and receiver antenna. Successful determination and estimation of a channel matrix that improves the quality of the signal detection at the receiver side of this MIMO communication. So the quality of this channel matrix can be strengthened by iterating it through a convolutional neural network or this deep neural network blocks iteratively. Once a training is done successfully for other signal detection, it may not be a problem, no latency. So instead of SVD, before this machine learning technique, SVD was used, that is a singular value decomposition. And that method is somewhat tedious, time consuming, and at the same time, for different scenario, we have to freshly estimate the channel. That takes the time and latency is also increased. But by using this deep neural network, that burden can be overcome, as well as once it is trained, there is no headache in the future detection. Okay, so this is MIMO. This can also be taken as a problem for project. So by this, I try to conclude and thank you all. Yes, any questions?
Thank you, sir, for the wonderful session and for giving us valuable insights on the importance of machine learning for wireless communication. Now, participants, if you have any questions, you can unmute yourself and you can directly ask. You can also post the questions in the chat box.
Yeah, that is also okay.
Yeah. So, any questions from the participants?
Hello, sir. I am Prakash Shetty. It was wonderful hearing you, sir. You have covered a wide spectrum in communication, starting from very basics to advanced also. Even though I'm not a communication man, it was very beneficial for me. I clarified most of the doubts. But one basic doubt I'll always have, sir. That is, see what happens, in internet connection and all, we say bandwidth, According to my perception, bandwidth is analog term. Say, for example, signal bandwidth means the spectrum, the frequency component it occupies. Channel bandwidth means the amount of frequency ranges it can transmit without distortion. But when you say digital bits, bit transmission, how you can relate bandwidth and more bandwidth means more bits you'll get, more higher speed you'll get. How will you relate, sir, actually, theoretically? How to relate bandwidth and number of bits per second transmitted on a channel in a digital? Is there any way of relating this?
Actually, bandwidth and data rate is related, sir. Actually,
I wanted to know what is the mathematical relation we can derive between them. Is there any possibility?
Actually, the data rate, or you can say it's a channel capacity, that is related to bandwidth by means of this channel capacity theorem. That is C is equal to B into log to the base 2, 1 plus SNR. SNR also comes into picture, sir. Okay. So channel data rate is equal to bandwidth into log to the base 2, 1 plus SNR. Yes.
So actually, bandwidth is an analog term, strictly speaking.
Yeah, and it is an analog term, no doubt in that. But these bits are discrete term, but this is abstract. Bit is abstract. Okay, we have to give it to a physical means by means of baseband modulation. Just rectangular pulses are mapped. Zero bits are mapped into rectangular pulses. Then only it is a correct meaning.
Oh, one more thing. Actually, if 5G internet, 5G mobile communication. Why there is a lot of hue and cry about it? Because I heard recently one of the film actress, Juhi Chawla, went to High Court, Bombay High Court, to get a stay on implementation of 5G in India. Even worldwide, if you see, many people who are fighting for ecology, they also oppose 5G. What is the main drawback, sir? Actually, why people are so much afraid of 5G?
In a very hurry, without any proper groundwork, they have launched this 5G. So, what are the assurance they have done given in the paper that is not achieved in the real? That data rate as well as the quality. That is why there is a cry. So that is why I have told all these odd Gs, 3G or 5G, they are a failure. Mostly 6G they will rectify and call it as a new one.
That is a problem.
Yes, sir. Mostly 5G is a failure.
Yeah. Any more questions from the other audience? Students, you want to interact with sir?
Thank you, sir, for answering
Thank you,
the
madam.
May I now request Dr. Govind Raj, Associate Professor, Department of Information Science and Engineering, to propose the vote of thanks.
Good afternoon, everyone. We have successfully completed the 4th session of 5-day faculty development program on recent trends in medical imaging and communication. And it was a wonderful session by Dr. Prashant Kumar H, Assistant Professor, NITK Surathkal on machine learning for wireless communication. And in the end, he has given some ideas related to projects also based on machine learning techniques in wireless communication. I extend my gratitude to Dr. Prashant Kumar H for sparing his time and sparing his valuable time. Thank you, sir.
Thank you, sir. Thank you all.
I thank this opportunity. I take this opportunity to thank our President, Dr. AJ Shetty, sir, and Vice President, Mr. Prashant Shetty, sir, and all of the directors of Lakshmi Memorial Education Trust for their constant support in organizing events at AJ Engineering College. And also, I am thankful to our principal, Dr. Shantaram Rai, sir, for his endless support. Thank you, sir. And I'm very grateful to Dr. Jnani for all his efforts from planning and execution of this 5-day faculty development program. I thank you, sir. I extend my thanks to all heads of departments, teaching and non-teaching staffs for their support. Also, I thank all the participants for being wonderful audience. Thank you one and all. Have a great day. Over to you,
Sir. Okay, sir. Thank you. Thank you.
Once again, thank you, Prashant sir, for your taking time out.
Thank you, Prakash Shetty, sir. Thank you, Jnani. Thank you, Shantaram Sai, sir. Govindraj, sir, everybody.
Okay.
Thank you, sir.
Okay.
The feedback link will be shared in a while. Okay. Dear participants, the feedback link has been shared. Kindly fill up the feedback form. So here we have come to the end of today's session. I request all of you to join the final day of FTP tomorrow. Thank you for your active participation. Thank you one and all. Have a great day.